All right, everybody can see that okay?
Yes.
Thank you. All right, so Big O is two things. One, it's an underrated anime from the 90s, and two, it is a way of understanding algorithmic efficiency. So when I say algorithmic efficiency, kind of what I'm talking about benchmarking. Has anyone encountered that word before, benchmarking? No?
In a general context of comparing what performance of whatever you're doing against certain standards.
That's exactly right. So that's what it is in outside of code, and that's what it is inside of code. Benchmarking is literally the act of timing your code and seeing how efficient it is. And obviously, fast code is better than slow code. If your code is slow, then your applications are going to be slow. And if your applications are going to be slow, that's going to make for some very unhappy users. So the faster your code, the better. And we're going to be, this slide deck is available to you, and we have some resources here. There's something called Pi Performance, which helps you measure the documentation for your own. It's a library for measuring the efficiency of your own code, and we also have a visualization. So we can just take a quick look at that. Probably gonna have to go through an ad. No, okay, great. So as you can see, this is a side-by-side comparison of different sorting algorithms. In the bottom left, we've got bubble sort. As you can see, compared to things like shell sort, quick sort, merge sort, and heap sort, bubble sort is not very efficient. So I'm not going to watch the entire thing because we'll be here for a while, but you get the idea that the faster your code, the better. If we want to sort something, it's better to use a quick algorithm like shell or quick sort rather than bubble sort. All right, so big O itself is the notation that measures the complexity of the function, not necessarily the speed, though the two are often correlated. So we always talk about it in terms of O of n. O meaning O is the complexity, and n is the input size. So these are kind of the most common forms this will take. So the best one is having an O of 1 because that means the speed of your algorithm doesn't depend on the size of the data set. It's constant. Thinking of a graph, if it's 1, it's just a straight line going across. O of log of n is okay. It just means if you have 10 times data, it means your code is 2 times more complex. And O of n is a direct correlation, meaning if you have 10 times more data, your code is 10 times longer, it's 10 times more complex. N times the log of n is, so 10 times more data, 20 times more time. And O of n squared so it means 10 times the data takes 100 times more time. And worst case scenario is O of the power of 2 to the power of n. And if you find yourself in a situation where your code is this point, you may want to start refactoring right away. So I'm going to be talking about a few of these. Log n and n log n are pretty uncommon. So I'm going to be talking about some of the more common ones: O to the power on, O1, on, and on squared. So O1, again, is constant time. So the amount of time it takes to run your code is a constant. Whether you pass in 1 argument or a million arguments, it's all the same. So we have an example ready right here. First element is red, takes an array, and just returns true if array 0 is red, or else it fails, or else it's false. So in this case, we could pass it an array with 1 element or 50,000. It wouldn't make a difference because we're only checking 1 element in the array. So again, O1 is something we should strive for. It's not usually possible if you're working with a large data set, but if we can get as close to 1 as we can, the better. And so we have a real life example here of a pigeon race versus the internet speed. Has anyone heard of this story before? Because it's a good one. So this is a true story that happened, I believe, in 2007 or 8, where a South African internet company was being, like, people were mocking it for how slow it was. And so they decided, okay, what we're going to do is we're going to have a contest to see who can transmit 4 gigabytes of data about 60 miles first. This internet company's broadband or a carrier pigeon. And so what they did is that they tied a data stick with 4 gigabytes of data on it around a pigeon's leg and had it fly 60 miles away. And the pigeon won. And a lot of people, obviously that was pretty humiliating for the internet company, but it does a lot to demonstrate what an O of 1 does. Because the pigeon, the time it would have taken it for it to get to its destination wouldn't have changed depending on how much data was in that data stick. It could have been, it could have been as little as 1 byte. It could have been, I don't know what the most storage you can put in a data stick is these days, but as long as it weighed the same, it wouldn't matter. The pigeon would take the same amount of time. The broadband connection, on the other hand, it's throttled by how much data you put in. The more data you put in, the longer it takes to get there. So if it was a very, very small amount of data, the internet connection probably would have won. But the bigger it got, the more likely it was that the pigeon won. So that's why we want a constant time, if possible, is that way everything works the way it should, it's all predictable, and you don't experience any slowdowns. All right, now we're going to talk about O of n, or linear time. So when we talk about O of n, the runtime will grow linearly based on what you pass in. I should have prepared like a graph example for this, hindsight is 20/20. But thinking of a graph, the line starts at 0 and just goes in a straight diagonal line all the way across the screen like this. I don't know if anyone saw that. So essentially that means direct correlation. So the bigger the data the more data you put in, the more complex it gets at a 1-to-1 ratio. So the example they have here is a does it contain it, so i.e. a search function. So it iterates through the array, for item in array, and then if item equals value, return true, else return false. The real life example here is mo money, mo problems, but that's not exactly very illustrative. But I do want to talk about one thing about big O notation as we're going through this, which is it's entirely possible in this function that we pass it an array of 50 items, for example. The item could be the very first value in the array, right? In that case, it doesn't take very long to run at all. But it could also be the very last item in the array, or not be in the array at all. If that's the case, then we have to go through the entire array in order to get an answer. And big O notation, when you're looking at your functions, always measures the worst case scenario. So at any point, something with an O of n could run very quickly if you're lucky, but we want to check what happens if you're unlucky. That's the most important thing. Okay, I'm getting a Slack notification. Make sure nobody's okay, Chase. Oh, thank you, Chase. All right, here we go. So this one doesn't have an O of 1 on it, or oh no, that was down there. So yeah, O of 1 is all the way at the bottom. O of n is more like this. This isn't how I would draw it, but this is good. This is a good example. So yeah, the further you get from here, the worse it is until you get up to this section. So stay away from here. All right, now we're going to take a look at O of n squared, quadratic time. So that's meaning that it increases exponentially over time. So this technically happens if you have a loop inside of another loop. So if we have a function that returns all possible combinations of items in an array, you'd say for number 1 in array, you loop through it. And every time you loop through it again. So you get number 1 and number 2. So in that case, you have n to the power of 2, which is bad. That's extremely bad, actually. But sometimes it's unavoidable. All right, yeah. So those are the three most common you're going to run into: power O1, On, and On squared. A few things to keep in mind as well about this when we talk about n is that we don't measure constants when we talk about this. So say, for example, in our linear time thing, what if we had 2 arrays and we had to loop through both of them? But not one array inside the other, just one array after another. Logically, I would say, okay, that means I have a big O of 2n. That's how you would think about it. But, and I guess you wouldn't be wrong per se, but if you said that in a coding interview, most people would say, well, that's just the same thing as n, O to the power On. Because constants, if you like start measuring them in like terms of astronomical data sizes, don't make that much of a difference. So in this example, 2 loops that just run one after the other, the big O notation would still be n, even though there are 2 loops happening, because we're just measuring, okay, if we pass in one large loop and one large data set, this is how it grows. So some key takeaways here is, 1, so all of these examples we've been using are using arrays. And the reason we're doing that is things like dictionaries, hashes, objects, whatever you call them, are always faster than searches through arrays because hashes don't keep track of indices. So that even if you are, unless you are looping through like, dot keys, it's much faster to search through one because it doesn't have to loop through the entire thing to get it. Again, whenever possible, avoid nested loops because that's how you get a O of n squared. And again, if you find yourself writing code that has poor big O complexity, consider refactoring it. And in general, so big O is something that I don't know how often it will come up as a developer per se. That's something you're kind of expected to keep in mind in your work kind of by default. It does come up very often in coding interviews. So you'll very often have a coding interview that'll, you'll either do it on a whiteboard or code live. And your interviewer at the end of it, once you've come up with your solution, will typically ask you, all right, so what's the big O complexity of this? And just generally keep in mind, chances are you can just say this has a big O complexity of n or n squared. And if you want to look up more examples of, all right, here's how how do I get to log n or anything like that, that's also available. But that is big O in a very, very small nutshell. Does anyone have any questions about this? Or I should say, what questions do you have about this?
I realize we don't have a whole lot of time, and this may be a more philosophical thing, but it seems like like I'm a big nested loop guy, so now I'm feeling bad about myself. But like it seems like even if like for all the things that we do to avoid nested loops, are still doing nested loops. So how does that improve the computational efficiency? They're just doing it with different notation, it seems like.
Are you asking how big O does that?
Well, I guess I'm wondering, so sometimes it seems like nested loops is what the logic calls for. And then like you can get away from doing nested loops by using different syntax and things like that. But it seems like that different syntax is still going to be going through things at the same amount of time. So I'm wondering how it can actually get better computational efficiency.
Good question. So yeah, sometimes nested loops are just the best solution. Like we say you should avoid, something with a big O of n squared. That isn't always possible. And you can't all, and sometimes you can't avoid it, and sometimes you'll use methods that actually have a big O complexity of n or n squared on their own. So let me try something real quick, see if I can demonstrate this right now. I'm going to take a look at this the pi performance here. So see if I can do a quick demo of this. So make sure I got to install it first. So I'm going to pip install pi performance.
You just said pip, you didn't say install.
Oh, thank you. And while that's running, I'm going to take a look at, see if we can find the documentation here. This might be a little more complex than I thought.
And again, it's fine for us to take this offline or in a follow-up thing. We don't need to. For my
Yeah,
sake.
no, it's something that's important. So I just want to.
Okay.
All right, so you'd say Python 3 pi performance. All right. So I'm going to make sure I'm understanding this right. So I'm just going to write def all combos, takes an array. And we'll just say combos equals this. I'm just going to copy the thing that our example with something with an n of big O of n squared.
You use brackets instead of parentheses for your definition.
Oh, thanks. All right, and then I'm going to run all combos on. Actually, let's try it this way. All right, so I'm going to be trying to get every combination of numbers 1 to 2000. So this is going to be probably pretty slow. And of course, it didn't open up in the right directory. 1 sec. All right. So now I'm going to look at this. So if I'm understanding this correctly, I should be able to do pi performance run and then the file. That's what I'm hoping. All right. So, all right, I'd have to spend more time with pi performance itself to understand how it is. It's not just running this. So in that case, I'm sorry, this example didn't really end up going anywhere. But let's see what happens if I run this file. Let's see if there's any.
There's no printing or any display, so it'll run. So the only thing you can measure is the time it takes to get you the new line in the terminal.
True, but you could already tell that it took several seconds for it to finish running. So if I do something like print. So, and I'm sure there are more efficient ways of going about this problem. I don't know them off the top of my head. but I just wanted to give you a demonstration of why this problem, this benchmarking problem, is real. Because something like, honestly, this isn't a super complex problem. It's a very easy solution to implement, but it's not an efficient one. Because, yeah, this is 2,000 this is 2,000 items, which in the grand scheme of things, by computer standards, isn't very big. And it's already taking several seconds to accomplish. And that's not what we want to deliver to our employers or customers. So I'm sorry that doesn't really answer your question as well as I hoped it would, but that's a good example. I'm glad I could show you a little bit of why this is important.
No, and I wonder, and I think Chris could weigh in on this. We ran into these kind of problems with Sudoku, and we ended up using sets quite a bit. So going forward, it might be interesting for what you did there to cast that array to a set to see how it compares to running it as a list.
Yeah, that could definitely be one way of handling it.
Because I think that's kind of what Steve was getting at, is you could do list comprehensions or for loops. It's really just syntactical differences. It's not performance differences, right?
Yep, exactly. This is all about performance. What? Anyone have any other questions about Big O and benchmarking? Yeah, so Julian mentioned that we could also have had a counter going to get the exact measure of how long it takes. Who here feels that if they went through some of their own code right now, they could say what the Big O complexity of it was?
I'm pretty sure I could.
Maybe in like 50% of it.
Yep, that's fine. So today, after the assessment, we do have some challenges to help you practice figuring out what your Big O notation, Big O is. So you'll have some practice with that. In that case, I'm going to stop right here. Let's take a 6-minute break, be back at 9 o'clock, so we can have our talk with Kelly.